Hello. In this short video, we will discuss a formula for the average value of a function using a definite integral. We will apply it to a specific simple example, and in the process of doing so, we will gain some insight into why this formula actually works, why it does find, in some sense, an average value of the given function. Look at the theorem box on the top here. It says that if I have a continuous function on a closed interval domain, then the average value of the function on that domain is given by this particular formula in the box here. Look at what it says. I would evaluate the definite integral of this function f between a and b on the endpoints of the domain. And then in the front, I would multiply by 1 over b minus a, or in other words, divide by b minus a. Let's try to parse that out and see what that's doing and why that works. So to start, let's relate that to what you would usually do to find the average of a data set. I made up a simple example here where I have 6 values, 3, 3, 5, 7, 8, 10. To find the average of that data set, we would add all of the values. In this case, I would get a total of 36. And then I would divide by 6, because that is the number of values in the data set. It is the size of the set. So for this example, I would find an average value of 6 for that data set. But think about the two steps that were involved there. Finding the sum, the total, and then finding the size of the set and finding their ratio. Think about how the formula given in the green box at the top is doing exactly the same thing. The integral is kind of like the sum, or it's the total area under the function f. We even talked about in class how the definite integral symbol itself is an elongated s, which comes from sum, for Riemann sums, for adding up the areas of rectangles and taking a limit, and blah, 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 all that stuff we discussed. So that specific part of the formula is just like adding up the values of the data set in that simple example. And then the dividing by b minus a step, well, that's like dividing by the number of values, or the size of the data set. In this case, b minus a is the width of the domain. It's like the size. So this formula really does exactly like what you would do for a data set. Another way to think about this is to pretend that the function f is a velocity function. In that case, we've discussed how the the integral of that velocity function is the displacement of the object. It's the change in location of the object over that interval of time from a to b. And in this case, b minus a, that's the amount of time that passes. And so what you would have here is essentially the distance, or displacement, or change in location divided by time. And that's exactly what your average speed, or your average velocity, would be. Just like if I said I went 100 miles and it took me 4 hours, then I averaged 25 miles per hour. Same idea happening here. So try to see this formula as not something random out of nowhere. It really does capture the average value of a function. Let's apply that to a specific example. Here I've chosen a nice simple x squared function, and we're going to find its average value on the domain 0 to 3. Now I've chosen that domain as part of the problem here. Anything you would be doing the domain would be provided to you somehow. I've also graphed this function on that specific domain. You can see that graph on the left for reference. To find the average value, I would have to set up an integral. I'm going to integrate this function between the endpoints of 0 and 3. And I'm going to apply the power rule to get an antiderivative. In this case, 1/3 of, going from 0 to 3. I'm going to plug in the lower and upper limits of 0 and 3. And I can see that I get 1/3 of 3 cubed is 27 minus 0. So I get a nice 9 after all that. That's the area under the curve. That is the area of this red region that I'm shading right now. That's what that 9 represents. The next step I need to do is the width of the domain, which in this case is 3. I'm going from A to B, 0 to 3, so the width is 3. So overall, the average value is 9 over 3. I get 3. A couple things about that. That's exactly the height of that horizontal line I have in the graph over there. That's the average height of this curve between the two endpoints that I've marked at x equals 0 and x equals 3. Another way to think about this is it says over 3 hours, I traveled 9 miles, so I averaged 3 miles per hour. Think of the 3, the width, as time, and think of the 9, the area under the function, as the displacement. And so this is saying that my average speed over that time was 3 miles per hour. Here's a little more about that specific example. You can see that I've colored a couple of the regions in the graph for some reasons that we'll get into here. My first question is asking, find the value c between 0 and 3 that makes the function output 3. So in other words, let's say f of c equals 3, and then let's solve for c. In other words, we're trying to find the x-coordinate of that particular point where the function, the graph, intersects the horizontal line that is the average height. So in this case, f of c is c squared. When does that equal to 3? Well, I'm going to get c equals root 3. Well, you know, technically speaking, c could be negative root 3, but that's not in the domain that we're talking about between 0 and 3. So I'm going to ignore that one. My second question is asking for the area of the green region down there. This is saying find the area between the two curves, y equals f of x, the x squared, and y equals 3, the horizontal line, the average height. Find the area between them from x equals 0 over to the point where we just found the intersection, where c equals root 3. How do I find the area of that green region? Well, that area we can find by evaluating some kind of definite integral. I'm going to integrate between 0 and root 3. Those are that is the intersection point we just found. And the function inside is going to be 3 minus x squared. Because across that region, y equals 3 is at the top, and y equals x squared is at the bottom. So let's see. Antiderivative is 3x minus 1/3 of x cubed. I'm going to go from 0 to root 3. So let's see. When I plug in root 3 at the top, I get 3 root 3 minus 1/3 of. Now, over here, let's figure out what root 3 cubed would be. That's root 3 times itself 3 times. Those first two factors alone multiply together to give exactly 3. So this entire product is 3 root 3's. And that's what I'm going to put in here. That's the root 3 cubed. All right, meanwhile, when I plug in 0, I'm going to get 3 times 0. I'm going to get 0 cubed. I'm going to get a big goose egg out of that. So I'm just going to say minus 0. All right, what's next? Let's continue evaluating. I have 3 root 3 minus 1/3 of 3 root 3, or just 1 root 3, minus 0. So that's 3 things minus one of those things. So I have 2 of those things, 2 root 3. That is the area of the green region in the graph over there between the function and its average value. Now hang on to that number. We're going to come back to that in a minute. Let's answer the third question. What's the area between the two curves, the given function and its average value 3, on the right side from x equals c, root 3, all the way over to the right end, x equals 3. Let's find that area. Well, I'm going to do pretty much the same thing. I'm going to set up a definite integral. This time I'm going to range from root 3 on the left all the way over to 3 on the right. And in this case, the upper curve is always y equals x squared. And the lower curve is always y equals 3. So I'm going to subtract them in the opposite order. So I'm going to get pretty much the same antiderivative as I did last time, but with opposite signs. And I have different limits this time, root 3 up to 3. Now when I plug in 3, let's see what happens. I get 1/3 of 3 cubed is 27, minus 3 3's. That's me plugging in 3 at the top. And then when I plug in root 3 at the bottom, I'm going to skip a couple of steps and say, you know what, this is exactly the same as what we did in the previous problem with opposite signs. You can look back at that work and pause the video to do that. But you'll see that it's exactly the same calculations, but we have a negative where we have a positive and vice versa. So I'm just going to skip ahead and say, you know what, when I plug in root 3 as the lower limit for this antiderivative, I'm going to get that negative 2 root 3, the opposite sign of what we got last time. So let's continue. I have 1/3 of 27, which is 9. 3 3's is 9, minus negative 2 root 3. So that's a 0 minus a negative, so I get positive 2 root 3. That's exactly the area of the blue region in the graph there. And in fact, notice that that is exactly the same as what we found for the other question we just answered. So what we're finding is that those two regions have exactly the same area. That's the sense in which y equals 3 is the average height. It splits that region between the curves into two equal-sized pieces. No other height, y equals 4 or 2 or 3.01 or anything else will do exactly that. Only y equals 3 splits those regions so that they're the same area.